Welcome to the Explainer. Today, we are diving into one of the most powerful tools in all of astronomy. We're talking about a single chart, just one graph, that completely unlocked the life story of the stars. So let's just rewind the clock for a second. Picture the early 1900s. You've got astronomers who have been working like crazy for years. They've put together these massive, dusty tables filled with data on thousands and thousands of stars. You know, how bright they are, their temperatures, all of it. But here was the big problem. It was just a jumble, a total chaotic sea of numbers. All this amazing information was right there, but it was so overwhelming, and there was absolutely no obvious pattern, no hidden order that connected one star to another. It was just cosmic data overload. So the big question for everyone was, how do you sort through all of this? How do you take this mess of data and actually make sense of it? Turn it into something that could reveal the fundamental secrets of how stars actually work. Well, that's where two astronomers, Ejnar Hertzsprung and Henry Norris Russell, had this incredible breakthrough. And here's the thing, they were working completely independently of each other. They both came up with what we now call the Hertzsprung-Russell diagram, or the HR diagram for short. And the idea behind it is just brilliantly simple. It's a graph that plots how bright a star really is, its luminosity, against how hot it is. All right, let's break down how this thing is set up, because it's important. The vertical axis, that's pretty straightforward. The higher up a star is on the chart, the more luminous or intrinsically bright it is. Simple. But the horizontal axis, the one for temperature, that one's got a little quirk. It actually runs backwards. The hottest, bluest stars are way over on the left, and the cooler, redder stars are on the right. Now that might seem weird, but trust me, that unique layout is the key to everything. So what happened when they finally started plotting all those thousands of stars onto this new chart? Well, they made an absolutely stunning discovery. The stars weren't just scattered all over the place randomly. Nope. Instead, they fell into these very clear, very distinct groups, almost like different star families. You could immediately see four main regions just pop right out of the data. Each one of these clusters represents a completely different type of star, or maybe a different phase in a star's life. So let's break them down, and we'll start with the biggest one. So the most obvious group is this long diagonal strip right down the middle called the main sequence. This is like the stellar superhighway. About 90% of all stars, including our own sun, spend the vast majority of their lives right here. These are the stable, healthy stars, all just happily fusing hydrogen into helium in their cores. Okay, now look up in the top right corner. Here, we find the giants and the supergiants. These are stars in a much, much later phase of their life. So after a star like our sun burns through all the hydrogen fuel in its core, it actually leaves the main sequence and moves into this region on the chart, puffing up to a colossal size. And that explains the paradox, right? How can they be cool but so luminous? Well, it's because they're just enormous. And then way down in the bottom left, we have the final act for a lot of stars, the white dwarfs. Now, these things are super hot, which is why they're on the left side of the diagram, but they're incredibly dim. And the chart tells us exactly why. If something's hot but not bright, it has to be tiny. And that's exactly what they are. These are the super dense, Earth-sized dead cores left behind after a star like our sun sheds its outer layers. So you see, the really crucial point here is that a star's position on this chart isn't just a random snapshot. It's like a chapter in its life story. The diagram doesn't just put stars in boxes, it actually shows us their life path, where they've been and where they're headed. You can figure out its size, its mass, and even guess its life expectancy, all from one dot. This chart also lets us instantly figure out a star's size. A star in the upper right is cool, yet it's super luminous. That means it's gotta be huge. A star in the lower left is really hot but very dim, which means it has to be tiny. You can almost think of the HR diagram as a map of stellar real estate. And for all those stars on the main sequence, the diagram reveals another profound secret: the link between a star's mass and how bright it is. Basically, the more massive a star is, the more gravity it has. That creates unbelievable pressure and heat in the core, which just supercharges its nuclear fusion engine, making the star exponentially brighter. A tiny increase in mass leads to a huge increase in luminosity. And you know, this relationship has a really dramatic consequence for a star's life. Because these more massive stars are so much more luminous, it means they are burning through their nuclear fuel at an absolutely ferocious rate. and that directly determines how long they're going to live. Think about it like this. A high-mass star is like a gas-guzzling Hummer. It's got a giant fuel tank, tons of hydrogen, but its fuel economy is just terrible. A low-mass star, on the other hand, is like a super fuel-efficient compact car. It has a tiny little gas tank, but it sips its fuel and can drive for a really, really long time. So who runs out of gas first? The Hummer. The massive stars, they live fast and die young.
Now, what's really cool is the HR diagram doesn't just tell us about individual stars, it also helps us understand the entire population of our galaxy. It lets us take a kind of stellar census to see what kinds of stars are common and which ones are incredibly rare.
And this leads to a fascinating little paradox, which you can see when we compare these two diagrams. So on the left, you've got a chart of our closest stellar neighbors. On the right, you have a chart of the brightest stars we see in the night sky. Just look at them. They look totally different, right? And that tells us something really important about our place in the galaxy. So it turns out that our cosmic neighborhood, our local block party, is pretty much dominated by the stellar equivalent of that fuel-efficient compact car. Most of the stars physically close to us are these faint, cool, low-mass stars called red dwarfs. A star like our sun is actually kind of an oddball in our immediate vicinity.
So why does our night sky seem so full of these brilliant, twinkling stars? It's because those stars are the cosmic Hummers, the giants and the supergiants. They look so bright to us, not because they're close, but because they are just intrinsically, unbelievably luminous. They're like cosmic lighthouses, so powerful we can see them from immense distances. But the thing is, they are exceptionally rare.
So the huge takeaway here is this. The most common stars in our galaxy, by far, are the small, dim, long-lived ones. And those brilliant, massive giants and supergiants that completely dominate our view of the night sky, in reality, they are the rarest of them all. Ultimately, the HR diagram just shows you the incredible power of perspective. With one simple chart, astronomers took a complete mess of chaotic data and turned it into the life story of the stars. It really makes you wonder, doesn't it? What other profound secrets of the universe are just hiding out there in plain sight, just waiting for us to find the right way to look?